SQL Server provides two data types to support spatial data, geometry and geography. Microsoft implemented these data types as system SQL CLR types. They're written in .NET code and use the .NET Framework and Common Language Runtime, or CLR. So these types do more than just provide a place to store data. They're rich classes with properties and methods that let you perform sophisticated manipulations of spatial data. Spatial data is a complex feature built on millennia of human map-making experience, with complex algorithms based on a variety of standards that support GIS applications and data. This course won't be able to do much more than scratch the surface of those features in SQL Server, but you should learn enough about how it works to get a feel for it so that you can decide whether it's appropriate for use with your applications. When working with spatial data in SQL Server, or just about any application that uses mostly two-dimensional spatial data, you'll generally use one of two spatial models, either the geodetic or planar model. The geodetic model is ideal for working with places and areas on the Earth's surface, and the planar model is best for working with XY coordinate systems of rectangular grids. These two models have a lot in common, but some very significant differences. The geodetic model is designed to locate objects on the surface of the Earth and allows for its non-spherical shape and uneven surface. This model uses latitude and longitude angles to locate positions on the Earth's surface. The difficulty in working with geographical data is that the Earth is not a true sphere. It's fatter in the middle, around the equator, because the Earth spins, and it has an uneven surface. Even though NASA photos seem to show the Earth as a sphere, that's really an illusion. So as you can see from this picture, it doesn't really show that it's wider in the equator, but it definitely is. And it's enough of a difference that it affects measurements when you're trying to plot locations on the surface of the Earth. You'll see various terms used for the shape of the Earth, including oblate spheroid, ellipsoidal sphere, reference ellipsoid, and sometimes simply spheroid. These are all attempts to put a name on something that really isn't regular or smooth enough to justify a geometric term. In fact, the shape of the Earth is unique, so many geophysicists use a word to specifically describe it, a geoid. Now, as a refresher, latitude is the angle north or south of the equator. Longitude is the angle east or west of the prime meridian, a north-south line that goes through both poles and Greenwich, England. And so here's a figure from the Australia ICSM that shows some of the relevant elements of the model for locating objects on the surface of the Earth. So you can see latitude and longitude, those are actually angles. You can see the ellipsoid or the spheroid, and then what's called the geoid, which is the red line. So that's the actual surface of the Earth. And then you can also see the spheroidal height, which is the difference between the ellipsoid shape and the geoid. And the line that shows the actual surface of the Earth, that shape is caused by various forces within the Earth, including plate tectonics, volcanic activity, and then other dynamic forces. So it's sort of a messy thing to have to work with, and particularly to try to apply geometric regular equations to. Now, SQL Server supports the geodetic model with the geography data type, which is a significant abstraction of the complex calculations that are required to work with geodetic spatial data. All right, then the other model is the planar model. The planar model represents spatial data in a flat two-dimensional plane and uses the Cartesian coordinate system grids that are rectangular. These are the grids that you probably sweated over in elementary or high school, plotting lines and shapes on x and y axes, and maybe a z-axis to hold a third dimension to the plots. The grids use uniform units of data, so that the number of units at the top of the plane is exactly the same as the number of units at the bottom of the plane. It allows no distortion, such as you might have plotting locations on the face of the Earth. The planar model is best for relatively small spaces, such as a sheet of paper, a warehouse, a plot of land, or even a city, which is pretty small compared to the entire surface of the Earth. And this model uses a two-dimensional regular grid to locate points and shapes. such as shown in this figure right here. And this is actually a screen capture of a shape that I created using SQL Server and displayed using the Spatial Results tab within Management Studio. Most importantly here, the distance between the lines is the same at the top of the grid as at the bottom of the grid. There's no distortion from any kind of projection. You can use the planar model with any coordinate system semantics that you wish, meaning that you can define whatever measurements you want to use, whether they're miles, kilometers, inches, or nanometers. SQL Server supports the use of planar data using the geometry data type. This type is quite similar to the geography data type, and even a bit simpler because it doesn't have to deal with the Earth's rough surface. The type abstracts all those geometry calculations that you may have learned in school, so you don't have to worry about finding those old textbooks before using the type. So that's the good news. It's often necessary to work with Earth-based maps on a two-dimensional planar surface. This is how Google and Bing Maps can display large geographical areas on the flat screen of your computer, and how the Auto Club prints a map of a country on a flat sheet of paper for your next road trip. There are a whole lot of ways to convert the spherical Earth to a two-dimensional system. Most maps on paper are a projection of a circular world onto a flat plane. This kind of projection always incurs some distortion. Since there's no perfect way to peel off the surface of the Earth, reduce it, and lay it on a continuous flat surface without distortion. Map makers have worked on the problem for millennia and have come up with many solutions, all of which are a compromise in one or more ways. Nevertheless, each kind of projection may be appropriate for different kinds of uses. For example, you're really probably not worried about that distortion if you're using a city map to get across town. Now, to understand the projection problem with displaying geographic data on a flat surface, consider this image. This image uses a Mercator projection, one of many ways to project the surface of the spherical Earth onto a flat planar surface. This particular projection distorts the sizes of land masses, but retains their overall shape. It does have the downside, though, of exaggerating the sizes of land masses that are further away from the equator. You also can't use this type of projection to accurately measure distances, since the curvature of the Earth is going to distort the measurement. So notice the sizes of Antarctica and Greenland, as compared to Africa and the main continental portion of North America. Clearly, based on examining this map, Greenland is slightly larger than Africa, a bit smaller than continental North America, and Antarctica is the largest continent of all, by far. And as a matter of fact, this particular image cuts off a good chunk of Antarctica at the bottom of the image. So the actual landmass is even larger than in the image. It dwarfs most of the other landmasses on the Earth. Okay, but here are the sizes of those continents and islands. And this is according to the continent and Greenland topics in Wikipedia. So Antarctica is about 13 million square kilometers. Greenland is a little over 2 million square kilometers. And North America is almost 25 million square kilometers. And Africa is a little over 30 million square kilometers. So as you can see by their actual land area, Antarctica is really just a bit over half the size of North America. And that includes Greenland, because Greenland is considered part of North America. And Antarctica is way smaller than Africa. And then Greenland is about 15 times smaller than Africa. So obviously this map is just wrong, right? Well, no, not exactly. The map I'm showing here is projected onto the flat surface in such a way that the land masses that are farther away from the equator have a larger apparent relative size. That's because as the surface of the Earth was peeled off, it was peeled off starting at the poles towards the equator, and so the areas around the poles had to be stretched in order to lay on the flat surface and show continuous land mass. So the further away they are from the equator, the greater the distortion. And that's why Antarctica, the only landmass on Earth that surrounds a pole and is therefore the furthest from the equator, is grossly blown out of proportion on this projected map. Another problem with projecting the surface of the Earth onto a flat surface is calculating the distance between 2 points. The surface of the Earth has different curvature in different locations, with the surface a different distance from the center of the Earth. That plays havoc with calculating distances on a flat map. So keep that in mind the next time you're out in the woods and looking at your map and trying to find out how far you are from the nearest bathroom. Okay, just little words of wisdom there. Further detail about the many map projections is way beyond the scope of this course. But the good news is that SQL Server spatial data types handle many of these issues for you. So you can rely on their calculations as pretty good approximations. Microsoft belongs to the Open Geospatial Consortium, or OGC, which is a nonprofit international voluntary consensus standards organization. SQL Server uses OGC's Simple Feature for SQL standards, which OGC's website describes this way. OpenGIS Simple Features Interface Standard provides a well-defined and common way for applications to store and access feature data in relational or object relational databases, like SQL Server, so that the data can be used to support other applications through a common feature model, data store, and information access interface. OpenGIS Simple Features are geospatial features described using vector data elements, such as points, lines, and polygons.